If you've ever opened up the Arduino software, you've seen them. These two simple, kind of empty functions that are just always there. Well, they're the foundation of every single project, and today we're diving deep into the heartbeat of Arduino, setup and loop.
Seriously, every single sketch, I don't care if it's blinking one little light or running a whole complex robot, it all starts right here, on this exact blank canvas. These two functions, they're totally mandatory. If you try to compile a program without them, the Arduino IDE will just give you an error. They are the absolute non-negotiable starting point for everything.
So, that's the big question, isn't it? They look so simple, almost insignificant, but they represent this incredibly powerful and fundamental structure in all of physical computing. So, what are their specific jobs, and how do they work together to actually bring our projects to life?
Okay, let's get right into it. The absolute easiest way to think about setup and loop is with a simple analogy. Think of it like a stage play. One function is for preparation, and the other is for the performance. One gets all the props and lights ready, and the other is the main show, the part that happens over and over and over again.
And what's so great about this slide is how clearly it lays out their different jobs. On the left, you've got setup. It runs only one time when the Arduino first powers on or when you hit that reset button. This is where you do all your one-time prep work, right? You're setting which pins are inputs or outputs, starting up communications, all the boring but necessary stuff. And then on the right, you have loop. And just like its name says, it repeats forever. This is where the main action is, reading sensors, controlling motors, making things happen.
And this right here, this shows you the entire life cycle of the program, from start to finish. The second you power on that board, any global variables you've made get set up. Then, setup runs its course, just once. After that, the program jumps into the loop. It runs every single line of code inside it. And as soon as it hits the end, whoop, it jumps right back to the beginning of the loop and starts again. This cycle just keeps going, endlessly, until you pull the plug.
All right, theory is great and all, but let's actually see this in action. We're going to write a super simple program that uses a counter to make the repeating nature of that loop function totally visible, right there on our screen.
Okay, first thing we're going to do is declare a global variable. We'll call it counter. See how we're declaring it outside of both setup and loop? That means the whole program can see it and use it. And a cool little thing about Arduino is that if you don't give it a value right away, it just automatically starts at 0. Pretty handy.
Now, inside our one-time setup function, we're doing a couple of things. First, we kick off serial communication with serial.begin 9600. That's just how we send messages back to the computer. Then, we set our counter to a starting value of 10, and we print it. Now remember, this part of the code is only going to run one single time. And here's where the magic happens. Inside the loop, we add 1 to the counter with counter++, we print out its new value, and then we tell it to wait for 1 second using delay 1000. Now here's the key. As soon as that delay is over, the function doesn't stop. It jumps right back to the top of the loop, and that counter++ line runs all over again.
And here is the proof. Look at the serial monitor. You see counter 10 printed just once. That was from setup function. Then the loop function takes over, printing 11, then 12, then 13, and on once every second. So what does this show us? Well, two really important things. One, the loop definitely repeats, and two, our global counter variable holds on to its value between each trip through the loop.
Okay, that was a cool little software example. But let's be real. The true power of Arduino is getting it to interact with the physical world. So let's see how that loop function becomes the brain behind reading data from sensors and making actual decisions.
I mean, at its core, this is what physical computing is all about. The job of the loop is to constantly check the state of an input, like this switch on the left. Is it on? Is it off? And based on that information, it then decides what to do with an output, like turning this LED on or off. The loop is what connects that cause and effect. It's constantly asking, what's happening? And then saying, okay, do this.
So let's move beyond just a simple switch. A perfect real-world example is the DHT11 sensor. This cool little device can measure both the temperature in the room and the relative humidity, giving us actual environmental data to play with.
And what's really fascinating is how it works. Inside, there's a component called a thermistor. It's basically a special resistor where its electrical resistance changes a lot based on the temperature. This one is an NTC thermistor, which stands for negative temperature coefficient. All that means is, as the temperature goes up, its resistance goes down. The Arduino is smart enough to measure that change and calculate the temperature. Pretty clever, right?
So how does this all tie back to our main topic? Well, the loop is the absolute perfect tool for this job. The DHT11 sensor can give us a new reading about once every second, so we can just program our loop to ask the sensor for new data every second, creating this continuous stream of environmental information. This is the foundation for everything from a simple weather station to a super sophisticated climate control system.
Okay, we've read data from the world. Now let's actually do something to the world. Let's move from just passively sensing things to actively controlling them by making stuff move with DC motors.
Now here's a really important point. You can't just plug a DC motor directly into an Arduino pin. It won't work. The pin just can't supply enough power, enough current to get it spinning. That's why we need a motor driver, like the super popular L298N module. Think of it like a bridge or maybe a translator. It takes the tiny, low-power logic signals from the Arduino and uses them to control a much beefier power supply for the motor.
But wait, how do we control the motor's speed? For that, we use a really cool technique called pulse width modulation, or PWM. Instead of trying to change the voltage, we just send a super fast series of on and off pulses. By changing how long the pulse is on versus how long it's off, we can control the average power going to the motor. The light switch analogy is perfect. Imagine flicking a light switch on and off incredibly fast. The longer you leave it in the on position during each flick, the brighter the light seems. For us, that means a faster motor.
And this is how we tell it which way to go. The L298N has something inside called an H-bridge. By setting its two input pins, we can actually reverse the flow of electricity through the motor. So if N1 is low and N2 is high, the motor spins one way. You flip them, and it spins the other way. And if you set both to be the same, either both high or both low, the motor just stops. It's a beautifully simple piece of logic.
All right, let's do it. Let's put it all together. We're going to see how setup, loop, sensing, and motor control all come together in our final project, a simple, awesome, two-wheeled robot car.
So here are the key players. You can see how all the pieces we've just been talking about fit together. We've got our Arduino brain, the L298N motor driver to be the muscle, two DC motors for movement, a joystick to be our eyes and ears, our input sensor, and of course, a separate power supply for those hungry motors.
So what's the loop actually doing inside our robot? It's the entire brain, and it's running this simple three-step process over and over, hundreds and hundreds of times every second. Step 1, read the joystick's position. Step 2, translate that reading into speed and direction values for the motors. Step 3, send those commands to the L298N driver, which makes the motors spin. That is it, a constant lightning-fast cycle of reading input and commanding output.
There's this great quote from one of the sources that just nails it. Our code, the code running inside that relentless loop, is essentially just flipping a couple of tiny electronic switches inside that H-bridge. That simple action, changing the direction of the current, is what gives our robot the ability to move forward, backward, and turn. It's a direct, tangible link from a line of code to real physical motion.
So think about it. We've gone from a completely blank file with just an empty void setup and void loop all the way to a functioning robot. This simple two-part structure is powerful enough to read sensors, make decisions, and control the physical world around it. The only question left is, what are you going to build with it?